So I am going to talk about different ways of thinking about solving this problem, right? The first one is actually something that doesn't use belief states. It's pretty straightforward, very nice way of solving this. Is basically so I'm going to call them history-based methods, but almost all the partial observable solution methods use history in some fashion or the other. But I call these history-based methods because they use history very directly. So what do they do?
Keep a track of previous steps.
And
Observations.
and then keep a track and do what with it?
Update the belief.
No,
Or not using belief.
I told you, right, this first method doesn't use beliefs. How else can you use the observations directly?
Policy.
We talked about it. We talked about it in the options case. When I talked about semi-Markov options, what did I say? Look at the history since the option started or something like that. Exactly the same thing. You look at history forever, right? So your state space will start looking really funny. Your state space will look like the first state is 0, 1, 0, 1. Okay. So the next state is for this, right? So the most recent state will be the last entry here, right? So and then you go back in history. You remember the whole history like this, right? So this is my state. So if I am learning a Q function, I will learn Q of
Why do we not need an action to define the state, the history over there?
Good point. If you want, you can use action as well. So the history can contain just the sequence of observations you have made, or it could also have the action. If you want, you can put the action inside. That's a good point. So you could also possibly do this. Right? So you could also have the history as action as part of the history.
What is the info you gather out of actions?
Huh?
I mean, having actions, what do you get out of it?
So the thing is, so 0, 1, 0, 1 and then 1, 0, 0, 1, I keep going up, right? So that is one thing. If I go up, I have 0, 1, 0, 1, then if I go down, I have 0, 1, 0, 1. That's a completely different interpretation. If I did 2 ups and I still get 0, 1, 0, 1, with a very high probability that 0, 1, 0, 1 is a noisy measurement. If I go up, I get 0, 1, 0, 1 and then I go down, I get 0, 1, 0, 1. That's probably the right thing. Right? Probably I went from here to here and then I came back here. But if it had gone from here to here to here and I still get the same 0, 1, 0, 1, there's something wrong, right? I could have done either this measurement was wrong or this measurement was wrong, or could be something even worse. My sensors could be stuck at 0, 1, 0, 1, right? So I could have been anywhere in the world. Right? So knowing the actions helps disambiguate those kinds of situations. So I just keep doing up, down, and I keep seeing 0, 1, 0, 1, 0, 1, that's fine. If I keep doing up, and I keep saying 0, 1, 0, 1, 0, 1, there's something wrong. So it's good to have the actions.
Can we limit the number of
Exactly, that's a good question. Yeah. What do you think we should do?
we should otherwise we don't limit the steps. If we don't limit, because then
Why won't repeat? I mean, we talk about episodic MDPs and things like that, right? So next time you start an episode, you start from the beginning, right? It's like keeping track of a game from when you started playing the game. But you have a point. I mean, why do you want to repeat? But so people see how this can be useful, right? Okay, what are the problems with this?
State space is very too large.
Huh?
State space is too large.
State space is very large, right? So large state space.
Episode can be very large.
Huh?
Episode can be very large.
Yeah, that's why it's large state space. Yeah. So if the episode is large, the length becomes large. Anything else? So if you are thinking of doing parameterized representations and things like that, your states have different lengths.
Cannot parameterize.
Right? Not only is the state space large, but each description is of unequal lengths, right? Anything else?
We might be wasting computation on states that have quite low probability.
I'll come to that in a minute. That is a wastage of computation. But states of low probability, I mean, yeah, that's a problem we have with MDPs also, right? I mean, if you don't visit them often enough, you are not going to waste computation resources on them. Right?
So if you have an equal state description, can we use some kind of HNM and convert it into equal length this thing and
Sorry?
can we use a HNM and then convert them into equal length features?
You could. Maybe. I'm not sure. I mean, given the way the field is moving, I would say you would want to use an LSTM and not a HMM. But yeah, you could think of sequence models for doing this history modeling. That's exactly what I'm suggesting to you guys to use. Talk to him later. Right? So one thing that you want to think about. So when do you think this will work? Is it a good idea? Will it always work?
Short episodes.
Huh?
Yeah, short trajectories or short episodes. It will be lower memory.
What is it that we require of a state in MDP?
Information to predict the next state.
Think of the math. What did he say?
Information to predict the next state given
Huh?
predict the next state given
Given?
an action.
What is enough? We have a specific definition for a Markov-ness, right? What is the definition?
Present state is
Huh?
Present state only determines the next
Next.
state.
Sufficient.
The transition probabilities has to be well defined.
These are all missing a point. Missing an important point. So they decided to nominate you as a TA, is it? You're missing one important point. Probability of ST plus 1 given ST comma AT is equal to?
given all
Exactly. So sufficient, enough, will determine the next state, all of that is fine, but only to the extent of what you could have done with the entire history. That is all I am asking for, right? I don't want the current state to have more information than I could have had by remembering the entire history. That's exactly what we are doing here. If you can remember the entire history, you are essentially in an MTP. Right? So you can't ask for anything more. Okay? Is it fine? Is it correct?
If you're remembering entire history, then how
I'm just remembering history of the part, this history of the observations, right? So here there is a very nice question about the broken vision system in the book. I don't think did we assign it to you guys?
it was given before.
Think about that now, right? I remember the history from the beginning, and the history is 01, 01, 01, 01, 01, 01, 01. Is that enough? I might as well be anywhere else in the world, right? So I don't get the state information per se, because there is a significant level of noise introduced in the observations. Correct? So assuming that remembering history is good enough, so it's assuming that I know where I was to start out with and remembering history is good enough, then this should be completely sufficient, but sometimes it's not. Okay. suppose my observations is such that, right, I set up a kth order Markov system. What is a kth order Markov system?
K last state.
It depends only on the k last state, right? Normally what we talk about Markov is first order, right? So kth order Markov is, it depends on the k previous states, right? So if my observations is such that I have a kth order Markov system, so for the last k observations, k can be however large you want, can be arbitrarily large, right? But if there exists a k such that if I remember everything it is Markov, then all of this will work. Okay, that need not necessarily be the case, as I just told you in the broken vision system, right? But then there is a question that asks you, is the broken vision system Markov or not, right, in the textbook, and the answer was
It's not.
yes, it is, because there is no underlying state space, right? So we just assumed that is all the state is, right? So we didn't assume that there was an underlying state space. The observations was the state, right? And therefore I can predict the next observation very clearly, right? It's going to be 0 1 0 1. Duh. Correct? In the broken vision system, I can always predict what the next observation will be. It will be a completely blank screen, right? I don't need history because it's broken. I know that it will not change. Therefore, it is Markov. Huh? What is someone?
Repairs.
Oh, that is a different issue. That's a different. Huh? What is it? That is not a.
We assume that the camera getting broken is
It-
something because of
It starts out being broken.
First we see one picture and
Yeah.
then we get broken.
Yeah.
Which means something happened and then we got broken. Something can happen and then we can again get the vision back.
Yeah, but we didn't put that into the problem statement, did we? So it's broken, it stays broken.
That has to be modeled in the MDP. That
What
there's
has to be
some
modeled in
action,
MDP?
The cameras got broken, so you can get hazy pictures. Those are another set of states. It was not mentioned.
Yeah. So they're not there. Not mentioned means it's not there. If you're making, you always know the rule, right? If you're making any assumptions about the problem, write the assumptions clearly and then write answers. So if you're not making any assumptions, then I don't know. But anyway, so getting back to this, so if your problem is kth order Markov, right, history is good. Right, having history is actually a useful thing to have, right? So but we still have the problem of unequal state distribution, state lengths, right? How can we fix that?
In these states,
No. This state representation is unequal.
But define the states to be a combination of the previous case. You define a new set of states which has k previous states and then define an action on that.
So there are many ways of fixing it. For example, if you use LSTMs, you'll actually get a fixed length representation and all that. But one simple way to do it is to fix your history. You're going to say that, okay, it's kth order Markov, I'm going to look at the last k states, and then if I have only seen 3 states so far, to fill it with dummy interval. Right, that should be like a no op kind of a symbol, right? That say maybe, I don't know, 1 1 1 1. Basically, I'm surrounded all sides by obstacles. That can never happen, right? So I can just put 1 1 1 1 as my symbol.
It could happen.
Right?
If all of them
Well, I can't move, right? I mean, what's the point?
but sensors can still report that state.
Sensors can still report that state. Yeah, sure. I mean, then pick another thing. Say -1 -1 -1 -1 -1, whatever. Right? So pick some sentinel kind of thing. Right? We know for sure it is not a state. Right? So then what would happen is, suppose my history is 3. Right? This guy will be reported as 0 1 0 1 -1 -1 -1 -1 -1 -1, and this guy will be reported as 0 1 0 1 0 1 0 1 -1 -1. This is full state. After this, everything will be fine. So there will be a small fraction of the history, a small fraction in the beginning, which will have this weird -1s, but after that, everything will be fine. Okay, that's good. And so we have also solved the large state space problem, large state space problem, right, by using this. And what about where did the wastage of computation come in? I was talking about wastage of computation. It still is there.
Technically, two state sequences are supposed to end at the same state, same actual state. We'll be computing it separately for considering them.
That's one part of it. So anything else? For example, let's go back to the noise-free scenario. If I have a trajectory of 10 states, right, and let's say state number 10 is where I am now, and state number 9, my observation was 1001. So do I need to remember 1 to 8? Right, because 1001 is absolutely localizing, right? So I know as soon as I see 1001, I know I don't need the history before that. So as soon as I am able to localize myself perfectly, the history before that becomes irrelevant, right? So localizing yourself perfectly is just one example. There could be other cases where some places you need a history of length 3, some places you need a history of length 2, some places you need a history of length 7, and so on and so forth. It might not be uniformly kth order Markov throughout, right? But once you decide that it is going to be kth order Markov, then you are stuck with keeping a k window history around, and since you are treating this k window history as your state, you are unnecessarily relearning the same thing over and over again. So there might be the first 5 states might be irrelevant, but every time I visit a different set of states in the beginning, I will treat it as a different state, a different observation state, right? So these things, wastage of computation, that's what I meant, right? So if you can fix that, that will be great, right? There's also another problem with using kth order Markov. Why? What is the other problem? Determining the k. So you might actually get the k wrong, in which case either you will be doing wasteful computation because you have a too large a k, or you will be missing out on important information because you chose a too small a k. Okay. So these are all the problems with these history-based methods, but history-based methods are very easy to use, right? You don't have to worry about too many complicated things. For example, you don't have to worry about a belief state, right? We already saw updating the belief state is a very complex operation, right? So we needed to worry about how would you do this updation, things like that. We'll talk about that depending on how far I make it today, right? So we'll talk about that. And right, so it's a lot easier to implement, intuitively easy to understand, and if your MDP happens to have a small k, it's a kth order Markov with a small k, right? These are pretty good at solving the problem. You can go ahead and do it that way. So there is one method which I am not going to go into in detail. So I encourage you to read. No, I will not ask questions on this in the exam. It's called the U trees. Right, U trees are proposed by Andrew McCallum. When was this? Long time ago. Right? I forget, 92 maybe. Yeah. So what he does in U trees, U tree stands for utile trees. So it basically he only makes distinctions in the so he treats all the states as just one thing to begin with, right? So just a single state. Your problem does not have multiple states; it just has a single state. And then as you make more observations and you get more rewards, he only makes distinctions, okay, that allows you to make better predictions of the rewards you are going to get. Okay. So I will not worry about everything else. I will only worry about the first bit I see. Okay. So if the first bit is 0 or 1, should I make a distinction based on that? Right. So I split it into two states. In one state the first bit is 0, in the other state the first bit is 1. Right. So does it make sense? Right. I mean, does it give me better prediction? If it does, okay, great. Now should I look at the second bit now, or should I look at the first bit one step ago? Right. So there are multiple things. I can look at more bits in the current state itself, or I can start looking at history. Right. Okay, I am mixing up two things. I am mixing up a little later work. So what Andrew did was the following. Okay, do I look at one step down? Okay, so what is the first state? So last state was 1001, right? So I don't need to look further back in history. I am done, because any further back in history I look, I am not able to make any distinction between the predictions, because as soon as I know that the last state was 1001, I know exactly what will be the outcome of each of those actions. So I don't need any further history. But then I look back and see that the last state was 1010. Right, now I need to look further, one more step back, right? So I have to look at 1010, I have to look one more step back. If it is 1001, I am done, right? If I look one more step back and it is also 1010, okay, then maybe I have to look back one more step, right, or look forward, like, so I have to look back one more step, right? So like that. So we will have to look at what the history is, see what is it that you observe, and based on that you have to look further and further back in the history, right? So this is essentially what he did. So he didn't say that I will always use a history of length 3 or always use a history of length 4. What length history I use depends on what are the actual elements that go into the history.
So, but this would require you to keep a trajectory of unknown length at any point of time.
I didn't tell you that U-trees was data efficient or memory efficient. Okay, it's not. It's in fact it requires a horrendously large amount of memory. In fact, U-trees as it was originally proposed by McCallum is also very wasteful of data. Right? He wanted to give some guarantees about statistical independence and so on and so forth. So what he essentially did was, whenever he makes a split, right, he kind of throws away all the data, and then he starts all over again. Okay, so that's pretty wasteful use of data, right? So it's not, I'm not using the same trajectory to determine multiple splits. That gives you independence in the tests, right, but also wasteful of data. So we need to come up with other mechanisms. The U-trees is amazingly powerful, right? He actually has solved non-trivial problems which the other methods for partial observability would struggle with, because given the kind of state spaces he's looking at, right? But he does do a very good job with that. So that's basically on history-based methods. So the second class of approaches, which I would call this is the QMDP like approach, because I can't think of a appropriate term for it, but QMDP is a prototypical example of such kinds of models. Is that you assume that the MDP is available to you. Yeah, you assume that you know the MDP. Okay. Since you know the MDP, what you do is go ahead and solve it. Okay, you solve the MDP, you get a policy. Then what's the big deal?
Use this policy to define your MDP.
No, you assume that you know MDP is known. So you have this POMDP model, right? I assume that my SAPR is known. I'll solve the problem. I solve the problem. I can solve, do value iteration, policy iteration, whatever you want, solve it. I get my policy pi. And now what happens? Huh?
You solve for the states, but not observable.
Exactly. So execution becomes a problem, right? So I can solve and execution is still a problem. So can you think of ways of fixing that?
Start defining the O function.
Yes, so I have the POMDP. I have the POMDP, right?
Do you have the MDP or the OMDP?
I have, let's say I have the POMDP. So I solve the MDP component of it. Now when I have to execute, what do I do?
Do it on the observation.
Because I learned the policy on the states, how can I do it on the observations? Okay, even if I want to do it on the observations, what should I
We
do?
don't have the state, we only have here.
Huh?
Yeah, we're assuming whatever observations we have are the states.
No, we are not. I said we have the POMDP. I take the MDP component of the POMDP and I solve it. So I have a policy defined on the states. Right, in the history based methods we are assuming we only have the observations as states, right. The QMDP, as we are assuming we are given a POMDP, we have to solve it, right. So we solve it, we find the policy, because I just take the MDP component out and I find the policy. Now how do I execute it?
Observations.
Let's say I found the Q function, that's why it's a QMDP. Okay, somehow I ran SARSA, I ran Q learning, or I ran value iteration on the Q function, right? I ran policy iteration of the Q function. Whatever it is, I have the Q star for the MDP.
We need a mapping from observation to system.
Exactly.
Belief.
Then I have belief. Somebody said belief.
Belief.
Huh? Belief. Exactly. So what do you do with the belief?
You can belief policy is like has state to action probability map.
Huh?
So P of S into pi of A given S.
P of
The
S.
probability of that state.
Yeah, use belief here. Be bell of S
Bell of S
into
the policy of A given S. And then we use that probability distribution to pick the action.
yeah, QMDP. It's a Q function. Use the Q function. So essentially what you do is you is the some kind of score for, right, and then the action that you pick would be
Maximum score.
so you are in the current belief state, right, or you can think of this as so you are in the current belief state. So what is the value of that for taking action A? The current belief state. Current belief state, the value of taking action A is essentially given by the sum over all states, belief of being in the state into QSA. Right, and then when you take an action, you basically do this, right? So now I have solved the Q, right, and converted that into a value function over belief states comma actions.
So this kind of solution would happen when you know what the states are, but an agent working in that environment.
So we will look at the other popular method of solving partially observable MDPs, right? Unfortunately, all the methods that are out there, except history-based methods, assume that you know the POMDP. Right, or you take a Bayesian approach to solving this, where you start off with some distribution over all parameters of the POMDPs, and then you try to solve using that. But in whatever it is, you have some kind of model that you are using, right? So given that you are anyway having a model, anyway the assumption you make is that you know the model where you are solving POMDPs. This is a very easy way of solving it. You just solve the MDP first and do this. What is the problem with this method though? You have to maintain belief over all states, for all belief state methods. So that's the only non-belief state thingy. Okay, everything else we have, we will talk about. We'll be maintaining belief states.
You need to have them.
Huh?
You need the MDP.
We need the.
MDP.
No, that's what I'm saying, right? If you don't have the MDP, you don't know anything about it. That's your only option.
We are having two policies. One is over the states, and then we are doing.
So when you are executing only one policy, yeah, but you are getting somewhere close.
Q learning anyway is off learning.
Huh?
Q learning is anyway of not following the same.
No.
How are you going to update the value functions of the original?
I've learned it, right? Do value iteration, do policy iteration, do whatever. You have an MDP, you know how to solve it.
We need to update our beliefs.
Yeah, that is there for any belief state method.
We still need
Hmm? since we solved the problem assuming that you would have access to the state at that point, and now you are only doing a heuristic for converting that into an execution policy, the policy that you execute might not be optimal for the POMDP. If you solve the POMDP directly, then you can find something that is optimal for that POMDP.
Given the answer.
Right? Given now the solution you have discovered is assuming that you would know the state at all points, right? So given the uncertainty in the states, that might have been a better action to pick in terms of the total reward that you get. I mean, if I had, for example, right, here is a very dumb way of thinking about it, right, which is actually not too dumb later, as you will see. I can take my POMDP, right, I have this way of computing the belief, right, so we will come to that, you had a gist of how to compute the belief. Now I can define an MDP where my states are the belief states, right, and the transitions between the belief states is given by the computation that I did for finding the belief states, right. That function will give me the transition probabilities, right. So given that this is the initial belief state and this is the observation that you made, right, so given this action you took or something, what will be the next belief state? In fact, that will become actually almost deterministic, right, because it's actually a computation that will determine what the next state is. So I'll have a belief state, I'll do some computation, I'll get to the next belief state, and now it's an MDP, right. I know the previous state, right, and then if I know the previous belief state, my current action will determine what my next belief state will be. So if I know the previous belief state, the observation, right. If I know the current action, I'll know what the next belief state will be, right. So now it becomes an MDP. I can solve it. And what's the problem with solving that MDP? I have a very high dimensional continuous state space. Right. If my originally I had like a million states, now my state is a million dimensional simplex. Right. So it's like a crazy state space, and I have to learn value functions on top of that. Right. So it becomes a little painful. So what we will see in the, I'm going to defer it to the next class. I don't have actually energy to teach the whole of POMDPs today. So what we will see in the next class is how to solve the belief state MDP in a clever fashion by making use of certain kinds of regularities that will be available in the value function of belief state MDPs. The very fact that the belief states are simplices, right, and the belief state is a simplex, and then the value functions have to be related in a certain way, right. So we will use those relationships and try to come up with an efficient way of solving POMDPs directly. So where you are essentially learning a action from history, learning a policy from history to actions. Right? So that's essentially what we will do when we solve POMDPs. Right? So such solutions where you are actually cognizant of the entire history of what has happened, right, and then making choices and knowing that there is a certain uncertainty in where you are, and being cognizant of that and making your action choices certainly yields better policies than something ad hoc like this. Okay, what is nice about the ad hoc thing? It's easy, right? It's much easier to implement, and turns out that in practice it actually yields good policies. They are not too bad, right? So people have tried in most real problems that you encounter, right? So things are not so pathological that this will perform very badly. In many real problem domains that you encounter, QMDPs seem to give you good enough solutions. So people actually like to use this. Only problem is you can't prove anything, right? So the third class of methods are directly solving POMDPs. So it requires setting up a lot of machinery for that. So we'll come to that later. But there are two classes of algorithms here. So one assume that the model, other one is a like a Bayesian approach, where you don't assume the model, right, but you assume some kind of distribution over all possible models, right, and then as you gather more data you try to reduce that distribution also, but at every point of time you can actually solve a POMDP even though you do not know the true model, right. You can solve some assumed model and use that to generate some kind of experience and use that experience to refine your probability distribution over the models. Okay. So, you could assume the model and solve it, right? Assume that you know the model and solve it, or you can take a Bayesian approach. Of course, you can take a non-Bayesian approach also when the model is not known, right. You can just do some kind of a frequentist approach, just count the number of times some things have happened and so on and so forth, but it is more fun. Okay. So, the last class of algorithms, which I will not cover a lot, right, but there is a video for you guys to look at. Can you ask them to link the PSR videos? Something called predictive state representations. They kind of turned the whole idea of history based methods on its head. So, what did they do? They said, why am I bothered about history? So, what do I need the history for? So that I can make better predictions about the future, right. So, instead of worrying about history, can I just look at how well can I predict the future, right. So, what are the things that I need to know about the future, right, so that I can predict everything that can happen in the future. So, the basic assumption here is, if you make certain assumptions about the dynamics of the world, right, I can do the following. I can say that if I knew what is the probability of, let us say, if I go forward 2 steps, I will get a wall from wherever I am. If I go forward 2 steps, I will get a wall. If I go to the left 5 steps, I will get a wall. If I go to the right 2 steps and go up 1 step, I will get a wall. So, if I know all of these, okay, what is the probability of these 4 things happening, then I know where I am in the world. Kind of makes sense, right. Instead of trying to know about the history, if I can make predictions about where I will end up at, if I do some small policy fragment, right, and I will make certain observations along the way, right. So, essentially if I say after 3 steps I will hit a wall, that essentially means 1 step no wall, 2 step no wall, 3 step wall, right. So, it is a sequence of action observations.
How many steps you look at?
Huh?
How many steps you look at?
Oh, that you decide. That you will have to decide based on the problem dynamics. So, they have mechanisms for coming up with the tests themselves, right. So, these things are called tests. So, what is the probability of north clear, north wall, okay, that is one thing, right, that is one sequence. So, action north, observation clear, action north, observation clear, action north, observation wall, that is one sequence. Likewise, action west, observation wall, that is one sequence. Then action east, no wall, action east, no wall, action north, 1 wall, right, that is another sequence, right. These kinds of observation action sequences are called tests. Okay. So, what they did was they said that predictive state representation consists of a set of tests, right, and the probabilities that those tests will be true. Right. So, if I have this collection of tests and their probabilities, that will determine what a state is for me. That is why it is called predictive state representation, right. So, what is the nice thing about it is, they do not assume that there is an underlying MDP like the POMDP does, right. They do not ever want to look at the MDP. It is like saying that, okay, I do not need all the history sequences, I will need only some of the histories, and that is enough to represent the world for me, right. So, in predictive state representations, we do not assume that there is actually an underlying state space, we only have these tests, right, and we say these tests are adequate for me to make any decisions I want in the world. There might be a true underlying state, we do not know, right, but that is a very powerful thing about PSRs. If you build PSRs on top of POMDPs, then you can show that they are as powerful as the direct POMDP solution methods, they yield the same solutions and so on and so forth. but the nice thing is PSRs can go way beyond the regular POMDP setting because they do not have to have any notion of what the underlying state space is, right. They can have, they do not need a state space.
So how are the probabilities determined?
See the video. So this was proposed by Satinder Singh and his group, and the video is by Satinder Singh, so we are getting it from the horse's mouth. So when Satinder came down here for the reinforcement learning workshop, so I asked him to do a session on PSRs, and he did. So that makes it, that means that I don't have to ever teach PSRs again. Right? So that's a cool idea. Unfortunately, it is hard to learn the PSRs, right? So history-based methods is easy. Just look back so many times steps and you just remember whatever you wanted to learn. But learning the PSRs turns out to be a little tricky. You can learn linear PSRs, right? So what I mean by linear PSRs are a set of tests from which I can recover the probability of anything else being true. Right? Suppose I gave you 3 examples, right? So north, 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 and then east, and then west, west, north, or whatever, right? I gave you 3 examples. Suppose using these 3 things, I can give you the probability of west clear, west wall. By using a linear combination of these probabilities, then they are called linear PSRs, right? And linear PSRs will necessarily be large. They will be, if there is an underlying POMDP, if there is an underlying MDP on which this PSR is defined, the number of linear PSRs, linear tests that you need, right, will be the same as the number of states. Right? The test that you need will be the same as the number of states in a linear PSR. But if you are able to define non-linear relations that can maybe products and divide one by the other and those kinds of things, right, you can even get a representation which is smaller than the number of states. Right? But then finding non-linear PSRs is incredibly hard. So we only have like existential proofs, but actually finding these things are very hard. Right? But this whole literature on predictive state representation is very interesting. If there is interest next semester, if people are around, we could think of looking at PSRs if there is interest. Right? But I am more personally inclined to look at more of the deep RL stuff, but we will see. So but I am not going to cover this in more detail. So if you want, you should look at the lectures. So next class, what is left is I am going to talk about POMDPs. Right? So we will just do that in more detail, and that will be the end of it.